One of the most important ideas in chemistry, and actually pretty much everything, is the geometry or shape of things. So the geometry of molecules is really, really important in how they interact with other things. And if you especially are going to do something like drug design or try to understand the biochemical workings of an enzyme, you're really going to want to be able to see the molecules in 3 dimensions and see their actual shapes and how they can potentially interact with other things. The geometry of a molecule is not instantly recognizable from the Lewis structure, but if you apply a theory called valence shell electron pair repulsion to the information that the Lewis dot structure gives us, then you'll be able to deduce the geometry. And so we'll go through how to do that. And an important idea, they used to try to count electron pairs, but that led to some misconceptions. So now we use the term electron domains, but each electron domain, which is either going to be an atom bonded to the central atom or a lone pair of electrons bonded to the central atom, but those 2 types of things will repel each other and spread out in space about the atom they're bonded to. So because the atoms are connected to each other with electrons, and those bonds are negative because they're a pair of electrons, they're going to repel the lone electrons, and things are going to try to spread out in space and minimize those repulsions. And then a really important idea that I didn't get immediately, but if you look at X-ray diffraction data and the rest of that, the lone pairs of electrons are invisible, right, to the experiment, but they definitely affect the shape of the molecule. And that's why we have to include both the lone pairs of electrons and the bottom bonded atoms in our visualization of the structure. And then another thing that's directly related to this is a little more difficult concept, but something called the hybridization, which is an important part of valence bond theory. But the hybridization of a central atom is a direct consequence of the number of electron domains attached to an atom. And I'll try to explain that as simply as I can later today, and then when we get into valence bond theory, we'll get into a little more detail there. So the first thing to know is the fundamental electron domain geometries. So if there's a certain number of electron domains, they will spread out in space about the central atom and give you a resulting structure. So if you have 2 electron domains attached to the central atom, that's going to result in a linear structure. So you can envision the central atom here, and a lot of times they'll use a dot for that, or maybe an A, a capital A. And then if the first atom goes ahead and bonds to it here, or the first electron domain, and the second one's trying to avoid the first one, where is it going to go? Why, 180 degrees away from there. And so you end up with this linear structure, the 2 non-central atoms bonded to the central atom, and them getting as far away from each other as possible, leads to this bond angle of 180 degrees. So there's a linear structure, and the appropriate bond angle to describe a line is 180 degrees. And this can either be a lone pair or an atom, avoiding the other lone pair or atom. So that's a really important thing. The electron domains are either atoms or unshared pairs or lone pairs of electrons. Alright, so if you have 3 electron domains, then you're going to have something called Trigonal Planar. And again, in a 2-dimensional canvas, a triangle is pretty easy to draw. I may not get the angles perfect, and it may not be as symmetric as I'd like, but there's a little triangle, again the central atom, with 3 electron domains attached to it. The fundamental bond angle you would have here is 120 degrees. And then if you have 4 electron domains, Now they're going to spread out into three-dimensional space, which is going to make this a lot harder to draw and visualize, and again the math to figure out the bond angle is a little more complicated, because when you get into 3 dimensions you're not limited to 360 total degrees, but you have a tetrahedral electron domain geometry. So when you have the central atom, and 3 of the attached atoms will be like in a tripod. I see it. Now I'm drawing this as if there's a wedge forward in front of the page for one of the atoms, or lone pairs. There's one going back. There's another one in the plane, so this is creating a little tripod, and then if you threw like the camera part on there, they go up to the top there. So there's one illustration of a tetrahedron, or tetrahedral geometry. And this bond angle, we could take 45 minutes to do the analytic geometry required to figure it out, but 109.5 degrees is the bond angle between any electron domain, the central atom, and the other electron domain. So atom, central atom's atom angle in a tetrahedron is 109.5 degrees. And this is pretty much all that you really need to know for organic chemistry, is these 3 electron domains, because those are the ones that the octet rule is obeyed. So I'm going to go ahead and put that on the side over here. For these 3, the octet rule is obeyed, and most organic molecules go ahead and obey the octet rule and stick to these electron domain geometries. So that's what you'll see for most of them. Now, if you have something that valence expands, then you can have 5 electron domains on the central atom, which will require at least 10 electrons on the central atom, and then you'll get a trigonal bipyramidal structure. And now the triangle will be a nice plane like the trigonal planar, that part. And then if you put an atom on top of that triangle attached to the central atom, then you can make a little pyramid on the top, then you put another one on the bottom. So there's a trigonal bipyramidal. The triangle part, you have the 120 degree angles, and then because the top and bottom are perpendicular to the triangular plane, you have 90 degrees there. So that's a structure we won't talk about a whole lot, because we're not likely to encounter it very much. And then this 6 electron domains, or our 5th electron domain geometry, is very symmetric. It's called octahedral, and a little sketch of that looks like the X, Y, and Z Cartesian coordinate axes. And here you have all 90 and 180 degree angles. So notice the right angle there, 90 degrees. This is octahedral electron domain geometry, and the 6 things about the central atom arrange themselves in a nice X, Y, and Z all perpendicular geometry. So there's our 5 electron domains, and the thing that's intimately tied to the 5 electron domains would be the so-called hybridization of the central atom. And what this, well, the way I think about this is certain number of orbitals need to get involved to bond the central atoms to the non-central atoms and to accommodate the lone pairs, and the number of electron domains you have to accommodate will dictate how many orbitals get involved in the bonding. So if you need 2 electron domains, you need 2 orbitals, one pointing in each direction, and the hybridization to achieve that geometry would be sp, from an s orbital and a p orbital getting involved in the bonding and putting this thing together. Now if you need a 3rd electron domain, you need another orbital. So you grab the s, which is the lowest energy orbital in the sublevel, and then you grab 2 p's. So sp2 means I have 2 p orbitals and 1 s orbital involved in the bonding and forming the hybrids, and that would be 3 orbitals, which is what you would need to accommodate 3 electron domains. For 4 electron domains, you need 4 orbitals, so you grab the s orbital and 3 p orbitals. So there's your 4 orbitals. And then if you go beyond that, so if you have 5 electron domains, now you need 5 orbitals, and you could see a lot of people would go, oh yeah, sp1, sp2, sp3, and they're ready to go sp4, to which you say, oh no, there aren't 4 p orbitals, there's only 3 p orbitals, so if you valence expand, you have to start using d orbitals, which is why only certain elements can valence expand, because if you're not in the 3rd quantum level or higher, you can't use d orbitals because they're not in that energy level. So for the 3rd row elements or beyond, they can valence expand, start using their d orbitals, and form sp3d hybrids. And then if you have 6 electron domains in an octahedral geometry, then you go with the s orbital, all 3 of the p orbitals, and 2 d orbitals to accommodate the 6 electron domains. You need 6 orbitals. So these electron domain geometries, when you start using d orbitals and bonding more than 4 things to the central atom, that's when your valence expanded. So here's 5 electron domain geometries. And once we understand the 5 electron domain geometries, understanding the shapes of the molecules that are possible from there is more straightforward. So there they are, the 5 electron domain geometries, and the idea that these geometries are going to allow us to understand the geometry of the molecule is really important.